In the last lecture, we had introduced the concept of a potential and talked about potential in a few cases. Today, what we want to do is to discuss the relationship of the potential with the potential energy. In general, we want to talk about how to calculate the electrostatic potential energy of a system of charges. So, let us review a few things which we started last time, and one of the things that we talked about last time, but could not complete was determining electrostatic boundary conditions. What happens is that at the interface between two media, for instance, supposing one medium is air or vacuum and the other medium is a charged body, you find there are certain conditions to be satisfied at the interface between two media, and these are known as boundary conditions. Till now, we have been doing electrostatics. So, what I will be concentrating today with respect to the boundary conditions, which will be elaborated more as we go along, will be the electrostatic boundary conditions. So, let me begin with assuming that I have a charged sheet, an infinite sheet for convenience I take, and there is a charge density sigma on this surface. So, it is an ideal surface in the sense that there is no thickness, and I know that if the charge density is positive, then the electric field above electric field sort of goes away from the direction of the charge. So, as a result, in this example, it is upward above the sheet and it is downward below the sheet. Now, to look at what boundary conditions we must satisfy, what we do is the following. We take a Gaussian pillbox, as it is called, or just a rectangular parallel pipe of an infinitesimally small width epsilon, and make it intersect so that half of this lies above the sheet and the other half lies below the sheet. Now, what we want to do is we know already, according to Gauss's law, that the flux out of any surface, real or imaginary, is equal to the amount of charge that is enclosed divided by epsilon 0. Now, in this case, let us assume that the area of the top surface is A, and as a result, if I want to calculate the total flux through the surfaces of the rectangular parallel pipe, you notice that I will take the epsilon going to 0, and as a result, what I get is how much is the Q enclosed? The Q enclosed, because I have said that the area of the top surface or bottom surface is A, and this sheet is without any thickness, and the charge density is sigma. So, this tells me that the amount of charge that is enclosed by such an intersecting parallel pipe is just sigma times A. So, integral E dot ds is sigma times A, and let us look at how to calculate this flux. So, you notice that as epsilon becomes smaller and smaller, since the area of all surfaces other than the top and the bottom becomes infinitesimally small, there is hardly any contribution to the flux from these surfaces, and by definition our direction of the normal is perpendicular to the outward perpendicular to the surface. So, that they are oppositely directed on the top and the bottom surface. So, as a result, the contribution to the flux from the top surface is the normal component of the electric field multiplied with this area A, normal component, because I have to find E dot n ds. So, So, as a result what happens is that from the two surfaces, because the direction of the top surface is opposite to the direction of the bottom surface, the normals are oppositely directed. So, I get E perpendicular above times the area A minus E perpendicular below times the area A is equal to sigma A by epsilon 0, which means that E perpendicular above minus E perpendicular below is equal to sigma by epsilon 0. What it implies is this, that if there is a charged surface, then there is a discontinuity of the electric field, the normal component of the electric field as you cross a charged surface. The difference between the normal component of the electric field above a surface and that below a surface is given by the charge density of on that surface divided by epsilon 0. So, the normal component of the electric field is discontinuous. Now, notice this is all about the normal component. Now, what happens to the tangential component, that is the component which is parallel to the surface? So, once again I start with the same surface, infinite sheet with a charge density sigma, and I am interested in looking at what happens to the normal to the surface. Now, this time what I do is this, I have a rectangle. The previous case was a rectangular parallelepiped, but this is just a rectangle, and this rectangle is of width epsilon, and which is again taken to be small, and length L, and I make it half above the charged surface and half below. Now, I know that because the electric field is conservative, the line integral of the electric field, which is E dot dl over any closed path is equal to 0. Now, so if I look at this rectangle and I take a line integral of the closed path, because by definition the direction along which you traverse is tangential to any curve. So, as a result E dot dl contribution from these two surfaces will be along the tangential direction, and there will be no contribution from the two short sides because epsilon is going to 0. And here you notice that I am traversing in one direction here and the other direction there. So, as a result E dot dl is E parallel above minus E parallel below times the length L, which must be equal to 0. As a result, the E parallel above is equal to the E parallel below. So, this what I notice is that though the normal component of the electric field has a discontinuity across a charged surface, the tangential component does not have a discontinuity. In other words, the tangential component is continuous. So, these are two boundary conditions that have to be satisfied at the interface between two media, where there is a charge sheet between on the interface. So, these were about the boundary conditions. So, let me now go back to a calculation of the potential energy. You might recall we had said that there is a connection between the potential and the potential energy. We had seen that if there is a charge which is located in an electric field, then the electric field of course is created by another collection of charges. Then this system has a potential energy, and there is a term which is, or in that potential energy there is a contribution because of this charge which is located at, let us say, the point r. So, this potential energy associated with our test charge, okay, if our test charge is taken to be a unit charge, is what is the potential at that point. So, this is the relationship between the potential and the potential energy. Let us look at it a little more quantitatively. To do that, I would take a collection of charges. To begin with, I will take collection of discrete charges, and suppose I bring in charges such that my final configuration is that the charge q 1 is at the position r 1, a charge q 2 is at the position r 2, etc., etc. How do I calculate? How do I calculate the potential energy of such a configuration? Now, so I will give you a prescription of what to do. We assume that initially all the charges are at infinity. Now, we have seen that it is good to take the reference point of potential energy to be 0 at infinite distances, because forces, the Coulomb forces vanish at infinite distances only, being a long range force. So, initially all my charges will be assumed to be at infinity and infinitely separated. Let me now do the following. Supposing now, because all charges are at infinity, there is no electric field in the finite region of space. So, what I do now is bring in a charge q 1 from infinity to and put it in its own location, which is r 1. Now, when I do that, no work is done, because this charge is not subject to any electric field, because it is the first charge being brought in from infinity and there is no field existing there at all. The situation changes when I bring in a second charge. So, suppose I brought in a first charge which is at the position r 1, and now I want to bring in a second charge. Now, this second charge will be placed here, that is with respect to an arbitrary origin. The first charge is at r 1, this will be placed there. So, let us look at, put that in. Now, notice that this second charge that we have brought in experiences a field, because already the first charge is in its place. So, what I need is, I have to do some work, because there is an electric field due to the first charge, and this will exert a force on the charge, the second charge that I am bringing in as it comes from infinity to its location. And in order to take care of or work in order to make sure that the charge comes and is located at the point r 2, we, meaning the external agency, have to do work to overcome this force. And I already know the charge, I already know the electric field, because the electric field is due to the charge q 1. So, therefore, the electric field at this position, which is r 2, is 1 over 4 pi epsilon 0 q 1 divided by the r 2 minus r 1, and directed, of course, along the line joining them. So, the work that needs to be done is to 1 over 4 pi epsilon 0 q 1 by r 2 minus r 1 times the charge q 2. Now, this work that you have done obviously will now become the potential energy of the system of two charges. Now, let us bring in a third charge. Now, so this third charge is brought into a position r 3. This is being brought into a position r 3. But now, this charge experiences an electric field due to the presence of both the first charge and the second charge. And since it is at r 3, so when q 3 moves to r 3, the work done is Q3 times electric field due to Q1 as well as Q2. This is what is written here. Now, I can go on like this, a fourth charge, a fifth charge and things like that. So what have we actually seen? What we have seen is that the amount of work that is done is equal to the amount of work that is done. Suppose we are looking at the work done in assembling n number of charges. So, this work done is 1 over 4 pi epsilon 0. Now, let us look at how much work is done in bringing, let us say, jth charge when all other charges are already there. So, let me talk about the presence of charge as sum over I. So, I have Q I by R I minus R j vector times Q j. Now, this is the amount of work that I will be doing if I bring in the jth charge and locate it at the position R j when a system of charges are in their respective place. Now, so it follows that in order to get the total work done, I must sum over j, so that each charge j is in the field of every other charge. But notice, in this sum there are some restrictions. The restriction is because R I cannot be equal to R j, because a particle does not exert a force on itself. So, let me write that I is not equal to j. There is another factor that I have to worry about. In this way of writing the sum, I have done a double counting, because I am counting I and j, because there is a double sum. So, each term is counted twice. It is not true that there is a separate term for interaction between I and j and that between j and I. So, to avoid this double counting, I need to put in a factor of half in this sum as well. So, this is the factor to avoid double counting. But now you notice that this quantity is equal to half sum over I Q I. Now, let me write this 1 over 4 pi epsilon 0 there, sum over j not equal to I Q j divided by R I minus R j. But this term here is nothing but the potential seen by the charge Q I at the position I due to all other charges which are located at the position j. So, therefore, this can be written as sum over I Q I times phi, the potential at the position R I. So, this is an expression for the potential energy of a discrete charge distribution. Now, what happens if I have a continuous charge distribution? So, for the discrete case, let me write it down again. For the discrete case, the work done is half sum over I Q I potential at the position R I. Now, it is easy to transform this, to the case of continuous charge distribution. For a continuous charge distribution, this sum over I will go over, I will take a volume and locate a small volume element at the position R, and the charge in that will be rho times the volume element, the charge density times the volume element. So, as a result, the natural extension of this expression is integral dq bar over the volume rho r. So, this is the volume, the charge that is contained in that volume element, and of course, the potential at the position r. So, this expression is one of the standard expressions for calculation of the electrostatic energy of a continuous system. Now, let me do some algebra. So, firstly, you recall that according to Gauss's law, divergence of the electric field E is rho by epsilon 0. This tells me that this rho there I can write as epsilon 0 times divergence of E. So, therefore, let us put that epsilon 0 by 2 integral dq bar del dot E times phi of r. But recall that E itself is minus gradient of phi. So, as a result, I get minus epsilon 0 by 2 d cube r. So, del dot of E gives me del square of phi times phi. Well, there are all these dependencies there. Now, I do a little bit of arithmetic with this, and what I will do is this, that I will look at this expression and notice the following, that del dot phi times del phi. So, divergence of a scalar times a vector is phi times del square phi. So, the scalar times divergence of whatever vector is there, del dot del is del square, plus gradient phi dot the second term, which happens to be also gradient phi. So, it is gradient phi dotted with gradient phi. So, I use this expression to simplify this term there. So, let us rewrite it. So, W is equal to minus epsilon 0 by 2 integral dq bar del square phi of r, and this is then by using this identity, what you have written down is given by, there are two terms now. So, come back here. So, del square phi times del square phi, which is what I have here, is del dot phi del phi minus del phi dot del phi. Okay? So, therefore, this term becomes equal to, there is a, I will take the minus sign first. So, that this is integral dq bar grad phi dot grad phi minus del dot of phi grad phi. Now, notice this term. So, now this is over, this is the work done in assembling a continuous charge distribution. So, therefore, this volume over which this integral is taken is the volume of whatever system that you have. For example, this could be your volume V. But notice something interesting. I need not confine myself to this volume V. I could as well take any imaginary volume, for instance this one. The reason why I could do that is because if you look at this expression here, number 1, you notice that it is a product of rho with the potential. And if I take the region to be expanded like this, in the intervening region there is no charge density is 0. So, the contribution to the volume integral will become 0. Now, if I take the volume over which I do this integration to be infinite volume, even then there would be actually contribution coming to that equation 1 which I showed you just now from the physical volume, because rho is 0 in the other case anyway. Now, however, if I do that, then this term which is del dot, so this is dq bar del dot phi del phi, which by divergence theorem gives me phi grad phi dotted with ds. In this I need to calculate, I need to plug in the potential or its derivative, namely the electric field, only on the surface. If I take the surface as going to infinity, then of course this term goes to 0. So, therefore, I need to concentrate only on this term, and since minus gradient of phi is the electric field, this expression gives me epsilon 0 by 2 over all space modulus E square dq bar, and you notice this is an integral over positive terms only. So, therefore, this quantity is by definition positive. This is a point which we will need to make comments on as we go along. Let me make a quick comment here, and I will come back to this issue a little later. The energy could be both positive and negative. For example, supposing I am putting one charge at one position and an opposite charge in another position, the potential energy is negative. But this being an integral over square of the electric field, it is always positive. Now, the problem has its resolution, which we will be talking about a little later, is because when we took the point charge, we assumed that no work was done in making a point charge. In other words, point charge was given to me, and as a result, what I am actually doing is not calculating the total energy in case of the charge distribution, but only the interaction energy between the charges. So, in discrete case, the work that is done to make a charge is not included. Now, we can actually calculate how much it is, because we have just now seen the work done is epsilon 0 by 2 mod by absolute E square dV, and now let me assume that I am talking about to create a point charge. So, this quantity then is E square. So, it is q square by r to the power 4th and r square dr. So, you notice this, that this one, this expression blows up at the lower limit. So, in other words, there is an infinite contribution to the energy, and this is normally referred to as the self energy. And when we calculated the energy of a collection of point charges, we never included this self energy. The calculation that we have done now, we have not yet actually done a physical calculation, but this expression and the corresponding discrete expressions differ by an infinite amount. This is what is known as a divergence problem in physics. we will not be making much of a comments on it, but we will make a few comments as we go along with our calculations. Now, let me now illustrate the calculation of the total energy of the charge distribution, taking a very specific example. And I will do this calculation of the electrostatic energy by 4 different methods. The problem that I have taken, simple problem, is let me calculate the energy of a uniformly charged solid sphere. In the last lecture, we had worked out the potential due to the charged sphere. So, let me recall it for you again. So, phi of r is 1 over 4 pi epsilon 0 q by r for r greater than the radius of the sphere, and we had obtained an expression like q by 8 pi epsilon 0 r into 3 minus r square by r square for r less than r. In my method 1, I want to start with the calculation of the energy by my first definition, which was this is integral over the volume of rho phi dq bar. Of course, I know what is rho. Since it is a uniformly charged thing, it is simply q divided by 4 pi by 3 r cube. So, uniform charge. So, charge q is uniformly distributed. Now, the charge density outside, even if you have taken a bigger volume, is 0. So, in this method, the contribution to the integral does not come from the whole space, but comes from the physical space. And so, therefore, it is only from the potential expression that I have to take should be the second expression here. So, if I plug it in, so since rho is constant, it will come out, and I am left with 3 q over 8 pi r cube integral. Now, only my integration is from 0 to r. The expression for phi there, which is q by 8 pi epsilon 0 r and 3 minus r square by r square dq bar. Of course, this integral does not have any angle dependence. So, as a result, I get 4 pi from the angle, so which I must plug in here, and then my integral is simply over r square dr. Now, this integral is very straightforward to work out. So, I can plug in, here is 3 q square, I had 8 pi into 8 pi, that is 64 pi square there, 4 pi goes. So, that is 16 pi epsilon 0, and of course, I have got a r cube and r. So, it is r to the power 4, and I am simply integrating from 0 to r 3 minus r square by r square dr. Very trivial integration to do, and you can plug it in very easily and get a result 3 q square over 20 pi epsilon 0 r. So, this is the energy of a collection of charges which give me a uniform distribution of charge in a sphere. Now, let us proceed with this. This time I will use the expression that we derived at the end, that is my method 2, which is work is epsilon 0 by 2 integral absolute E square dq bar. And I told you that because the surface term was thrown out, I had taken the range of integration to be infinite. So, therefore, this integration is over all space, not just the physical space. If you wanted to confine to physical space, which we will do later, we will have to keep the surface term as well, because the surface term was thrown out by taking the integration to infinite volume, and of course, we found that that is perfectly legitimate, because the charge density excepting in the physical volume was 0. Now, so in other words, I need the expression for the electric field. Now, this we know was trivially calculated by Gauss's law. The electric field expression for r greater than r was as if the entire charge was concentrated at the center of the sphere. So, it is vector r by or unit vector r by r square, Coulomb's law, and that is for r greater than r. For r less than r, because only small r cube by capital R cube amount of charge is enclosed. So, the field is linear, and this was 4 pi epsilon 0, and this was vector r by r cube, and that is for r less than r. So, I need to take both these contribution. So, within the sphere, I have this expression, outside the sphere I have that expression, and so I get epsilon 0 by 2. Once again, all these expressions do not have any angle dependence. So, my volume integral always gives me a factor of 4 pi. Integral E square. So, let me take that is q square over 16 pi square epsilon square. R dot r is r square by r to the power 6, and of course, r square dr, which comes from the volume element, and this integral is from 0 to r. The second integral is 4 pi r to infinity, once again this q square by 16 pi square epsilon square, and this time it is 1 over r to the power 4 and r square dr. Once again, these integrals are fairly straightforward to do, because this is just an r fourth integral, which gives me r to the power 5 by 5. This is 1 over r square, which gives me 1 over r on integration, and infinite limit will go away, because 1 over r goes to 0, and only this term will be there. You can add it up and find out that the result is same as before, namely 3 q square by 20 pi epsilon 0 r. Let us look at a third alternative. The third alternative that we talk about is to include the surface term, that is, do not take the range of integration to infinity, just confine yourself to the original expression. If you recall, this is half dq r rho r phi r, and we had changed this, to get an expression of this type, that epsilon 0 by 2 phi r E dot n ds, this was the surface term which we had thrown out, and of course, the volume term, which is this. Now, what is the difference between this expression and the expression that we worked out just now? Here, the surface is the physical surface, which is the bounding surface of the physical volume. So, in this case, I have to take the surface and the volume to be the physical volume, and once again I need both the expression, both potential at r, and I only need for r less than r, and this we had seen is given by q by 8 pi epsilon 0 r times 3 minus r square by r square. This we had used a little while back, and the electric field which we also used just now is given by q by 4 pi epsilon 0, and this was vector r by r cube. So, let us look at how does it go. My work done has two terms. One is epsilon 0 by 2 integral over the surface, this time my physical surface, phi of r vector E dotted with n ds and plus epsilon 0 by 2 integral E square d q bar over the physical volume. Now, notice that in this expression, I need the values of quantities on the surface, and the electric field is directed along the normal because I have a sphere. So, as a result, this term is epsilon 0 by 2 phi on the surface, magnitude of electric field on the surface times the surface area, which is 4 pi r square, plus epsilon 0 by 2, and this is the integral only of this part. So, the integral over the volume of q square by 16 pi square epsilon 0 square and r dot r, which is r square by r to the power 6, and of course, 4 pi times r square dr. Once again, this integral is straightforward, which we have done some time back, and here phi of r, you notice if you put r is equal to r, this is simply 2 q by 8 pi epsilon 0 r, and E of r is of course q by 8 pi epsilon 0 1 over r square, capital R square. So, you can plug these numbers in and once again show that this is equal to 3 q square by 20 pi epsilon 0 r. So, this is a third method of doing it. The difference between the first, second and the third method is that in the third method, we confine our integrations both over the volume and over surface of the physical sphere, whereas in the previous method, we had conceptually or we had imagined that let us take the integral over all space, and in that case the surface term vanished, but there was a cost, and the cost was that the volume integral has to be done by taking the electric field all over the space. There is still a final way of doing this, and this is a little interesting way of doing it, that let us do it from the first principle. Let us do it from the first principle. And what is first principle? The first principle is I have a sphere which is being built up gradually. That is, I bring an amount of charge dq from infinite distance and I spread this charge over uniformly over a sphere that has already been created. Suppose at a given instant of time, I have already a sphere of radius, let us say small r. It has been created by the same process as I am going to describe now. Now, what I do is this is a sphere of radius small r. Now, I bring in charge, small amount of charge dq from infinite distance and spread over this sphere uniformly, thereby making a second sphere, a sphere, or thereby increasing the radius of the sphere by an amount dr and the charge on that sphere by an amount dq. So, this is what we do. So, there is this charge which is at infinite distance and it is going to come there, and once it has come there, I am going to spread it over this by increasing by an amount dr. So, the question is this: how much work was done in bringing this charge dq from infinite distance and spreading over the already existing sphere. So, you notice that I had a sphere which had a radius small r. As a result, it already had a charge which is q of r, and I know that since the total final charge will be capital Q, the amount of charge q r, q as a function of r, is q small r cube by capital R cube. What is delta q? What is dq? dq is the extra amount of charge that is contained in a shell of which the spherical shell which lies within radius r and r plus dr. So, therefore, the amount of charge dq is the surface 4 pi r square times dr, that is the volume of the shell times the density rho. And if you put all this thing in, you find dq is 3q over r cube r square dr. Now, how much work is done? The work that is done is dw, which is equal to dq times potential at r, and I know the potential at r is 1 over 4 pi epsilon 0 times q of r by r. Remember that this shell is put outside the sphere. So, as a result, it is as if the field appears as if the entire charge q r is concentrated at the center. So, this is 1 over 4 pi epsilon 0 q r dq by r. Now, so what is my total amount of work done in assembling this entire charge distribution? This w is then simply, I have to simply integrate over the sphere from a radius 0 to a radius capital R, and this is all I need to do. This is all I need to do. This q r I plug in from here, and then of course, now remember that this is simply the integration is over dq, and there is just an integration is to be done over dr, and this gives me again 3q square by 20 pi epsilon 0 r. So, this is assembling the charge layer by layer. This is assembling the charge layer by layer. So, what we have seen is the following, that the charge if I have a continuous charge distribution, I can calculate the energy in different ways. In fact, I have shown you 4 different ways of doing it. But let me now come back to this question. Let me now come back to this question which we talked about in the beginning, and that is, there is a difference between the discrete charge distribution and the continuous charge distribution. We had seen that in case of continuous charge distribution, the integration is over modulus of electric field square, which is always positive. On the other hand, for a discrete charge distribution, the energy could be both positive and negative. Now, this is an anomaly, and we have to give an answer to that question. The answer lies in the fact that, as I mentioned earlier, that for a discrete charge collection, I never question how the discrete charges were made. So, as a result, supposing I go back and look at this expression that epsilon 0 by 2, my energy is epsilon 0 by 2 E square dq bar. Now, let me say that I have just 2 charges. Let me say that I have just 2 charges. Now, I know what is the field at any position r due to these 2 charges. Supposing I have a q1, so I have a q1 by 4 pi epsilon 0 r minus r1 divided by r minus r 1 cube, plus that due to the second charge, which is q 2 by 4 pi epsilon 0 r minus r 2 by r minus r 2 cube. Now, notice this is the electric field due to charge q 1 or q 2 at the position r. Now, if when you take the square of this, notice that electric field satisfies the superposition principle, but square of that does not. So, I will have terms which are E 1 square and I will have terms which are E 2 square, and if you calculate these two, they will turn out to be infinite, which is what I have been calling as the self energy. It is the cross term which, if you calculate it properly, will give you the energy that we calculated for the interaction energy of the two charges before. So, the difference between the two methods is due to the fact there is an infinite contribution to the self energy, which is neglected in our first method of calculating energy due to discrete charges. We will continue with this comment, little more elaborate on it, do this calculation next time.